Our first speaker, Nick McKeown, is Professor of Electrical Engineering and Computer Science at Stanford. Nick is well known in the industry, and in addition to his work at Stanford, Nick co-founded several networking startups, as well as the Open Networking Foundation and the P4 Language Consortium. Nick is also the lead on a major new initiative called Project Pronto, which was just announced recently. I'm excited to have Nick with us to share insights into this significant new initiative that is poised to have a dramatic impact on our industry. So with that, Nick, welcome, and please take it away.
So thank you, Timon. It's a pleasure and honor to be here today. And the context of my talk is really this Project Pronto, a DARPA-funded project that's with several of my colleagues, Nate Foster at Cornell, Jen Rexford at Princeton, Guru, Larry, and Oz at ONF, and the whole Pronto team, which is a research team across all of those organizations. So Pronto has the prime goal of figuring out how to secure our national internet infrastructure and our 5G infrastructure, obviously very much in the news at the moment. But our technical contribution to this is to explore how the network will be beneficial as a programmable platform, primarily to those who own and operate big networks. And so that's really the topic of today. Here we are in 2020, a difficult year, but let's put that to one side for a moment and think about what the network will be like in 10 years' time. So in 10 years' time, clearly the network is going to be very different from how it is to today. But it helps to think about how it was 10 or even 15 years ago to give us a sense of how much it will change over the coming years. Because if you think back to how it was at that time, there really has been quite a change. And that first change I want to discuss is a change of who is in control. You remember how networks were closed and proprietary, dominated by network equipment that looked like mainframe computers that were bloated and power hungry. There was very little incentive to improve them because of the industry structure. And so we talked of internet ossification. And as a consequence, network owners considered them hard to manage. They were, as we remember, unreliable, hard to secure, and very hard to scale. Well, along came data center companies, and they saw things differently. They started to build their networks from white box switches, controlled remotely from servers that were running a control plane within the Linux operating system. They were essentially homegrown networks for the first time, made possible because of the emergence of merchant switching silicon. They were Linux-based because Linux by that time and over the last few years has become a really acceptable way to build network infrastructure. And we have seen the rise of more and more open source in this arena. As a consequence, they've become easier to fix. Google, when they first described the SDN networks in 2012, noted that they could introduce whole new versions and revisions every few weeks rather than every year. They could add new features of their own, like traffic engineering, to get more efficient use out of their networks, doubling it in their case. They can introduce methods to recover faster from failure, detect the kinds of intrusions they were seeing in their networks more quickly, and overall just introduce faster innovation because the software was under their control. So we think of this phase of change as a change of who is in control. Network owners have taken control of their software. And today we take it for granted that they can write their own software, they can download it from somewhere else, an open source project, tailor and modify it to their own needs, and then share it with the industry as a whole. So this has been the last 10 years that we're very familiar with. More recently, and you may be less familiar with this, the network owners are beginning to take control of how packets are processed too. Because if you think about it, unless you're in control of how the packets are processed, you're not really in control of what your network is doing. What's happened is fixed function switches and NICs are starting to be replaced by programmable switches and smart NICs from a number of different vendors. They could be programmed using a language like P4 or alternative language, and we'll see many types of design over the coming years. What essentially has happened is fixed function pipelines like this one here with pipeline stages dedicated to certain functions are starting to be replaced with programmable versions. The problem with these fixed function pipelines is if you take a switch or a router in which there's a switch operating system controlling a switching chip, it would have applications for each of the protocols that run on that device, and then a pipeline in the fixed function switch chip that matches each of those stages. So each of the protocol stages that we would see in the packet headers. Over time, as network owners have taken more control of the software, they want to add new features to their networks. And when they do this, they can very easily add new software that sits alongside the other protocols. The problem is they often want to introduce new pipelining stages because of new headers that they introduce. Think of VXLAN or segment routing just in recent years. And as a consequence, they need to change the chip. In the past, this would take 3 or 4 years and maybe $100 million. So there wasn't really much incentive to make that change. As switch chips have become more programmable, this has become much easier. And as a consequence, we're seeing a trend now of domain-specific processors in networking. The computer that we all know has had domain-specific versions for graphics, for signal processing, for machine learning, and now we're beginning to see it for networking. In the past, we didn't have a language that we could use or a domain-specific processing pipeline. Nowadays, we can use P4, and the PISA pipeline has emerged as a programmable forwarding paradigm for the P4 language. So while it used to be the case back in 2010 that programmable switches ran 10 times slower, consumed more power, and cost more, this is in fact not true anymore, and there have been a number of demonstrations of commercial switch chips that run at the same speed, consume the same power, and have the same area, and therefore the same cost basis. So this is in the process of changing right now. So in this phase 2, we say network owners have taken control of how packets are processing too. We're kind of in the middle of that change, but that change is going to continue over the next few years. In addition, we've seen the rise of open source. And this really is quite a dramatic change. It's kind of happened perhaps without us noticing too much, because back in the past, we were familiar with open source running on our computers, but now it's really re-emerged as a legitimate and trustworthy way to control our networks as well. We're familiar with some of these names like Open vSwitch, Sonic, FBOSS, FRR, ONOS, and many, many more. What essentially has happened is that network code that was opaque and closed and proprietary is in the process of becoming more transparent and open. Now, I realize this is a slightly aspirational statement. We hope that it continues, and part of our project is to make this happen more and more over time. But if you look at the trend over many, many open source projects, starting from Linux back in the mid-90s, as soon as the merchant switching chips came along in the mid-2000s, we've seen this explosion, this proliferation of new open source networking projects that allow us to now build open source infrastructure, our network infrastructure, even at huge scale. And as it's become higher quality, more people have got behind it, more people have adopted and used it, then the quality has allowed us to now trust this to have sufficient quality. And now we see large organizations, foundations like ONF, the Linux Foundation, and TIP getting behind this too. Everything I've said so far, you may be sitting there and thinking, yeah, I know that already. There's nothing new there. That's a trend that I'm well aware of. And I agree with you, and I'm really here to ask the question, so what happens next? And that's really what our project is all about. There is something that happens as a consequence of this. The first is that for the first time, we can think of the entire forwarding pipeline from end to end as being programmable. So not only are the switches now programmable in P4, we've seen the emergence of SmartNICs that are P4 programmable, and vSwitches as well. And we already have user space configurable networking stacks based on DPDK, and in the kernel using XDP. So we're already in a situation where all of the networking forwarding plane is programmable and changeable by the owners and operators of networks. Not only is this happening, but we're well aware of the other change, and that is that the control plane is increasingly under the control of the operator as well. Well, individual pieces have been happening kind of in front of our eyes. Perhaps what we haven't noticed is suddenly the entire forwarding plane is programmable end-to-end and top to bottom. This has to have some profound effects on the way that we build networks. And we think that most of those consequences are good. First of all, I think we're going to think of a network as a programmable platform. Instead of thinking of it as a collection of boxes, we will think of it as an entire programmable platform that we can change and modify as we wish. We're going to describe the desired behavior at the top, and then partition, compile, and run the software across elements all the way down to the way that packets are processed. The largest networks will go first. Cloud, ISP, and 5G networks, we believe, are going to be programmed and tailored locally by those who own and operate them. And who better to improve the reliability and security of networks than their owners? They're the ones with the biggest incentive to do it. They're the ones with the most experience of what needs to be done. And they're the ones who are in a position to compete with each other by introducing differentiating new capabilities into their networks. One way we think that they will do this is to introduce fine-grained per packet measurement. This is already happening to some extent through in-band network telemetry and other fine-grained per packet measurement techniques that are being used to monitor the function and performance of networks. This is sort of the first killer app that people have started to introduce. But once the system is a programmable platform, there's some other interesting things that we can start to do. One is to start using software engineering techniques that have been developed for computer systems and have in the past been off limits to networks. I think they're going to start to be used routinely. So formal verification methods across state and across programs, and then on the fly dynamic checking of the correct behavior of the network. All with the intent of making future networks that will be programmed by many and operated by few. So where does open source fit into this? Well, we believe that it's going to be open source from end to end and top to bottom. Not in every case, but in large networks that we will have that choice. Networks for the first time, we believe, will be programmable end to end, specified top to bottom, defined entirely by software. And this creates new possibilities to verify that the networks are correct by construction, to measure and validate in real time against the original network specification, and then correct bugs through closed loop control. Now, I realize I'm stepping into the research domain by saying this. You can't look around and see examples of this happening today. And this is the research component of our Project Pronto. And the reason that we get to take part as researchers, as universities, is because of open source, that we, the research community, get to take part, because now you can build large production quality systems from open source software coming from organizations like ONF, which is what really makes all of this possible. And one of the most exciting aspects of this for us and for our students is that 5G is being redefined by software too. There is something different about 5G. It lends itself much more to the introduction of these ideas, open source software in control, and also software-based forwarding pipelines that are specified in languages like P4. So all of these things mean that this platform extends to 5G as well. How do we think it will happen? Partly through fine-grained telemetry of instrumenting every packet so that we can see what it's doing. Verification to check that every packet and all of the state is correct. And then by closed loop control, so that if we need to, if we detect problems through our fine-grained telemetry and our verification, then we can update the state and the programs. What do I mean by this? I mean that the specified behavior will be compiled, we will partition it, and we will push it down into the forwarding elements. And then from there, we will introduce fine-grained per packet telemetry to look and observe at what the network is doing as packets flow through the network, and then feed that back to compare against that specified behavior and potentially modify state or modify the entire program structure if that's what we need to do. Our initial Ether deployments, and the Ether platform is the platform from ONF that we're starting from, is going to be deployed in 4 locations shown here on the left, at ONF, at Stanford, and then on the East Coast, Cornell and Princeton. And at those locations, we're going to be deploying essentially the system shown here. So it's the Ether platform with 5G deployed on those, at those locations and at those campuses, with a programmable forwarding plane, with a fine grain per packet telemetry. And then on top of that, as researchers, we're going to be adding in this closed loop control in order to be able to experiment with new ideas, to demonstrate that you can really introduce closed loop control into systems like this. If you'd like to find out how to get more involved and to learn more, for sure, please watch Jennifer Rexford's talk about closed loop control and Nate Foster's talk about verification. Hopefully those will answer many of your questions that I'm leaving you with and not having time to answer right now. You can find the prontoproject.org website listed here, and that's really talking about the research portions of this. All of this is being built out on the Ether platform, and you can learn more about that from Ozone and Larry Peterson talk, which is coming up next. They're going to be describing the Ether platform. You can learn more about that at etherproject.org, or just come and join us. And I'm serious about this. If you're a university campus and you'd like to deploy an Ether Edge on your campus and then use it for research, you can build on top of it. You can modify, demonstrate new ideas in your own environment. We would love to have partners who are interested in doing that and working with us. If you're an enterprise, think about planning a trial or a POC for a 5G connected edge cloud on your in your network, both as a trial to start with, and then think about where a CBRS-based 5G network may fit into your campuses. And then if you're part of the supply chain, then join the Ether open source project, because you can contribute, you can use, modify, and then make that available to your customers by being part of that program. So I'm going to leave it there for now, and happy to take any questions. I realize this is kind of a whistle-stop tour, and I appreciate your patience as we go through and sort of unfold each of these projects in turn. But super happy to take questions, and I'll hand it back over to you, Timon.
Nick, great, thank you very much. So we do have a couple of questions, and there's some in kind of this range of verification. So I wonder if, I think verification is new in the networking space. I wonder if there's some examples of verification you might be able to share, maybe from other domains, that might help people sort of better understand or visualize how verification might apply in networking.
Yeah, no, that's a great question. Formal verification methods have been adopted by the semiconductor industry for a long time. When chips are designed, you start from a high-level description and then go down through successively fine-grained descriptions as you get closer and closer to the transistors. And as you go across each domain, across each abstraction, as you go down through synthesis and then place and route, it's typical to run formal verification tools to check that the behavior is the same above and below that boundary. And so formal verification methods based on essentially Boolean algebra have been in use for many, many years. In the software domain, then formal verification for checking the correctness of code, looking for things like buffer overflows, have been used with great success in many programs, and are used a lot within the automotive industry, in the military and defense industry, for checking the correctness of code against a set of invariant properties, and to make sure that they that they don't cause problems. Now, increasingly, we're seeing this in vehicle automation, autonomous vehicles, etc. And so there's a large pressure to develop and use techniques like those. And as systems get more complex, these become more essential. So in networking, where we have big, complex systems consisting of millions of lines of code, is ripe for this. But in the past, closed and proprietary techniques, closed and proprietary interfaces have made it off limits to those who own and operate networks. So I think that there's a huge amount of opportunity here for formal verification.
And another just follow-up question is, verification scope. Is it end-to-end or is it within the operator network or within a single system?
Great question. So in our Pronto project, we are planning to sort of explore, in fact, we have research ongoing in techniques that are local within an autonomous system, where you can identify, for example, very, very short-lived congestion events that you wouldn't normally be able to see, and then say, they shouldn't be happening. Let me figure out how I take corrective action way before a human could get involved to be able to go back, see that this has violated some SLO, and therefore go and fix it in real time. Another one would be, what if I see a packet that's in a location of the network where it doesn't belong? I may be able to see this through fine-grained per packet measurement, and in which case I can take corrective action because this violates some requirement or specification, and therefore I'll go back and fix the state or the failed piece of networking equipment that caused that to happen in the first place. Now, the things I'm describing are kind of in the research domain. They should be feasible within the next year or so, but you're not going to start seeing these in production deployment for another 2 or 3 years yet.
Very good. So let's see. A question about if we're using the intent-based declarative approach and applying it to the networking fabric, are we suggesting that per packet telemetry would include runtime performance in the compilation of the declarative state?
So there are actually networks, quite large networks, that do this already. If you're familiar with the P4 programming language, there are cases where cloud operators are including in the forwarding programs that they run on their programmable forwarding switches, they include the ability to generate metadata that the switch is aware of and make it available on the outside. It could be, for example, timestamps, queue occupancies, the table entry that the packet matched on. So all of this information can be carried out of the switch on the packets as they leave. This is usually referred to as in-band network telemetry. And these are programs that are just compiled along with the general forwarding programs that run on the switches. That then generates a, kind of a fire hose of telemetry events that then need to be picked through either by another switch or a set of servers looking for erroneous events. And so these examples that people have done today are generally looking at a sample of the data. Over time, though, as these techniques prove their worth, we're anticipating that a larger and larger fraction of the traffic will be examined this way. And in which case, you may even get to the point where every single packet is carrying telemetry information with it, making us able to almost entirely reconstruct the behavior of the network and capture almost any failure event that takes place.
Very good. So let's see. So, the transition you're mentioning is relying entirely on fine-grained packet, per packet telemetry. It's, however, something that's not available in the optical domain. So can you speak maybe a little bit about how that translates into the optical space?
Sure. In the optical domain, generally, because it's much simpler, we don't have per packet processing. One could argue that there are fewer things to go wrong. I don't mean to simplify the number of events that can take place, but we're generally looking for things related to continuity of the signal, continuity of the circuit or the channel, and less about the per packet events. So long as we can identify things that go wrong, things that we're looking for, we can either use that to feed it into the telemetry system, or even look for the next place where packets are traveling and then insert those as metadata onto those packets, whatever is most convenient. In our environment, we're not currently looking at the optical domain as a means of carrying packets. We're looking more at the RF and the 5G and the cellular, as well as the wireline packets. But that's going to be a good topic for us to look at in the future.
And just maybe closing with a question around research. What would you recommend to researchers in the SDN space regarding the effects of AI and ML and fine-grained telemetry?
Yeah, so once you've got this immense amount of telemetry and this immense visibility into what the network is doing, the sky's the limit in what you can do. I mean, we've built networks for years with a shockingly small amount of information. Most networks today are debugged using traceroute and ping, the same tools that we used 25, 30 years ago. Increasingly, though, as people get their hands on per packet information, they start to do some pretty exotic things with it. There are the mundane, looking to see what the queue occupancy is, so looking for short-term buffer overflow events, and then entire network information that is usually beyond the scope of a deterministic model that you're more likely then to put into an AI or ML system that is matching on known problems that it's seen in the past. We're anticipating that in the early days, we're going to compare the telemetry against deterministic models that we have derived from the code that specifies the behavior of the network. We think that's a good place to start, because once we have those types of models, then perhaps we can generalize to more statistical observations that will come from machine learning. But we think that the telemetry is going to introduce a massive number of possibilities like this in the future.
Great. Well, Nick, unfortunately, we're not going to be able to get to all the questions, but I think great talk, a great interest out there, and really an exciting area. So thank you for being with us today.
Thanks so much.